In this lecture of solid state devices, we will discuss about the second carrier transportation mechanism in semiconductors, that is diffusion process, and we will derive the diffusion current equation. In the previous lecture, we have studied the drift mechanism occurring in semiconductors and also derived the drift current equation J is equal to sigma E, the drift current density J is equal to sigma E, and we defined conductivity sigma as Qn mu n plus Qp mu p, where mu n and mu p are the mobility of electrons and holes. So the two carrier transportation mechanism in semiconductors are drift and diffusion. So drift occurs due to the applied electric field, and this diffusion mechanism occurs due to the concentration gradient in semiconductors. So we will discuss this diffusion mechanism with an example. So if we consider our classroom, and if we have a spray bottle in our hand, and if we open the spray bottle, the spray molecules will spread uniformly to the entire classroom, assuming there is no external disturbance for the air present in the classroom. So this process is known as diffusion. So or we inject a spray bottle, then the spray molecules will spread uniformly after 2 or 3 minutes. It will spread uniformly to the entire classroom. So actually this process is an example for diffusion. So if we have excess carriers, then the carriers will move from a region of higher concentration to lower concentration. So we have already studied about the generation mechanism of excess carriers, that is through optical generation we can generate excess carriers. So we can define diffusion as the charge carriers that move from region of higher concentration to lower concentration. That type of motion is called diffusion, and the current due to this diffusive motion in semiconductors is known as diffusion current. So when excess carriers are generated non-uniformly in a semiconductor, the carrier concentration vary with position in the sample, as we explained, similar to that of the spray molecules spreading in classroom. So this process of movement of charge carriers from a higher concentration region to a lower concentration region, this type of movement is known as diffusion. So now we will consider the spreading of electrons in a semiconductor. So we are considering a semiconductor, and excess carriers are generated in this semiconductors. So this is a semiconductor, and excess carriers are generated in this semiconductor, or we are injecting a pulse of electrons to this semiconductor. We are injecting pulse of electrons to this semiconductor. Then we can see that at time t is equal to 0, at time t is equal to 0, or at x is equal to 0, so this is the position, this is x position of the semiconductor, and we are measuring the concentration n of x. So this is x is equal to 0, and at time t is equal to 0, we are injecting the pulse of electrons to the semiconductor. So actually this is the concentration, electron concentration at time t is equal to 0. This is shown in this graph. So this is at time t is equal to 0. As time changes, as we discussed in the case of that spray molecules, the spray molecules will spread uniformly to the classroom. So it will change its position, the molecules will change its position. Actually this diffusion occurs due to the collision mechanism occurring in the semiconductor. So that carrier will collide with another particle and it will move. So this spreading occurs due to collision or scattering mechanism between the two particles. So this change we can observe at time t is equal to t1. So at time t is equal to t1, if you observe the concentration of electrons, then it will spread uniformly to either sides. So at time t is equal to t1, we can observe the spreading of electrons like this, and at time t is equal to t2 it will spread like this, and after some time then the spreading of electrons will be constant, or it will be uniformly spread, similar to that of the spray molecules that is spreading in the classroom. So after some minutes we can see that the entire classroom will be with the uniformly spread with the spray molecules. Similarly, these semiconductors will be uniformly distributed with the charge carriers. So this is the distribution of electrons, or the spreading of electrons in semiconductors. So this is at time t is equal to 0, the concentration will be maximum at the injected area. So at time t is equal to t1, the electrons will spread uniformly to either sides, and at time t is equal to t2, and the spreading will continue, and after some time the spreading of electrons will be uniform, so, or it will be a constant. So for deriving the diffusion equation, so we consider the one-dimensional view of the spreading of electrons, and at time t is equal to t1, if you observe the spreading of electrons, it will be like this, t1. So there is equal probability of moving electrons to the left or to the right. So we can see this is a symmetrical with respect to this zeroth axis, so it will be a symmetrical curve. So we are considering only one half of that distribution. So this is the one-dimensional view of n of x, and since it is symmetrical, we will consider only the one half of that distribution graph, and we will divide the distribution of n of x into different segments of equal length L bar. So this distribution graph is divided into different segments of length L bar, where L bar is the mean free path or mean free length, or it is related to collision. So it is a mean free, similar to T bar, mean free time for collisions. L bar is also related to collision, so it is a mean free length, that is L bar. So this distribution n of x is divided into segments of length L bar, and we are observing two segments, 1 and 2, segment 1 and 2, that is the shaded portions. So if we see this graph, this curve is going through the center of each segments. So we are considering only the segment 1 and 2 for deriving the current equation. So actually this is the segment 1 and 2. So we are expanding the view of figure A, considering only that segment 1 and 2, and we can see the segment 1, the concentration is represented by N1, and for segment 2 it is N2. So actually this curve is going through the center of each segment. So this is concentration N1 and this is concentration N2. So we can derive the current equation through this analysis. So actually we have two segments, segment 1 and segment 2, and n of x evaluated at the center of this n1 and n2. This is n of x. This is segment 1 and this is segment 2. And we can mark this point is x0. This point is x0 and this point is x0 plus L bar. Since the width of each segment is L bar, this point is x0 plus L bar and this point is x0 minus L bar. So if you see the difference, then it will be L bar on both sides. So x0 is considered as the middle point of these two segments. In one mean free time, so one mean free time, that free time and free length, that is mean free time and mean free length is related to collision. In one mean free time, half of the electrons in segment 1 will cross x0 and it will move into segment 2. So half of the electrons will move from segment 1 to segment 2. We know that the spreading is uniform, so it will move on both sides. So we can consider in one mean free time, half of the electrons move from segment 1 to segment 2 and half of the electrons will move from segment 2 to segment 1. So from 1 to 2, half of the electrons will cross x0 and from 2 to 1, half of the electrons will cross through x0. So we know that the electron concentration in segment 1 is n1 and the electron concentration in segment 2 is n2. Therefore we can say the total number of electrons in segment 1 can be written as, so we say that half of the electrons are moving from segment 1 to 2 and half of the electrons are moving from 2 to 1. So there is equal probability of moving from left to right and from right to left. So we can say that the total number of electrons in segment 1 in one mean free time, it can be written as n1 into L bar into A. And similarly, the total number of electrons in segment 2 can be written as n2 into L bar into A. The area of cross section is assumed to be same. So n1 is the concentration of segment 1, n2 is the concentration of segment 2, L bar is the length of each segment, that is also same. So the number of electrons in segment 1 is n1 into L bar A and the total number of electrons in segment 2 is n2 into L bar A. And equal probability of moving left to right and there is from movement from right to left. So we can say the net flow of, so half of electrons move from segment 1 to segment 2. Similarly, we can say half of the electrons move from segment 2 to segment 1 in one mean free time. So that is important. In one mean free time, this is the condition. There is equal probability of movement of electrons from segment 1 to 2 and from segment 2 to 2. So if we see the net flow of electrons crossing x0 in positive x direction, that is from segment 1 to 2, half of the electrons are moving. The next half is from 2 to 1. So if we consider the net movement in positive x direction through x0, so we can say that the net number of electrons crossing x naught, crossing the point x naught from left to right. Left to right, that means positive x direction. Positive x direction. So we are considering the net movement in the positive x direction in one mean free time. One mean free time. That is equal to, so half of the electrons, half into n1 into L bar into A. So half of the electrons is moving from segment 1 to 2, that is from left to right. Then net motion means the remaining electrons, that is from 2 to 1. 2 to 1 means right to left. We have to consider it in positive x direction, so we have to change the direction, that is minus half into n2 into L bar into A. Actually it is divided by T bar. T bar we are considering it as one mean free time. So this is the net movement of electrons. So we can say that half into n1 into L bar into A minus n2 into L bar into A. So this is the net movement of electrons in the positive x direction in one mean free time. And so if we consider we can define the electron flux density. We can define electron flux density. Electron flux density phi n of x. So electron flux density means it is the net flow of the net number of electrons flowing in positive x direction. Positive x direction per unit area. Per unit area means so rate of flow of electrons, so by time into area of cross section. So this is the electron flux density. So we can define the electron flux density as the rate of flow of electrons in positive x direction per unit area. So net number of electrons flowing in positive x direction. So we have already area of cross section, flux density, this value is 1. So we have to consider the area of cross section as 1. So electron flux density means this value will be 1. It is a rate of flow of electrons per unit area, that is known as electron flux density. So this term should be, actually area should be 1 for defining electron flux density. So this is half into the net flow of electrons in positive x direction, that we have already defined as half into n1 into L bar into A minus n2 into L bar into A. So this is the net flow of electrons in the positive x direction. So this can be substituted here, half into n1 into L bar. So area is unity, so it can be 1 minus n2 into L bar by T bar. Area is 1, or substitute the value of A and cancel by the denominator's term. So this is the value for the electron flux density, or this can be written as L bar by 2 T bar into n1 minus n2. So L bar by 2 T bar into n1 minus n2. So I consider the area of cross section as unity in defining flux density. So It is a net flow of electrons per unit area per unit time. So this is the equation, L bar by 2 T bar into N1 minus N2, and this is equation number 1, phi n of x, electron flux density. This segment length L bar is a small differential length, and so we can write N1 minus N2 as, so actually N1 is the concentration, so N1 is the concentration of segment 1, N2 is the concentration of segment 2. So we have to, there are many number of segments, so we have to consider all these concentration in terms of n of x. So if we define the concentration of N1 as n of x, then we can define the concentration N2 as n of x plus delta x. Delta x means the change in position. So this is n of x and N2 as n of x plus delta x. So by substituting N1 n of x and N2 as n of x plus delta x and dividing by delta x, so we have to multiply by delta x. So I multiply with the L bar. So N1 is replaced by n of x, N2 is replaced by n of x plus delta x, and dividing by delta x and multiplying by delta x. So delta x, instead of delta x I put L bar in the numerator, and with an assumption delta x is approximately equal to L bar, and so we can write N1 minus N2 as n of x minus n of x plus delta x by delta x into L bar, since L bar is a small differential length. So this can be written as L bar into n of x minus this term, n of x minus n of x plus delta x by delta x. So since delta x is tending to 0 or delta x is a very small value, we can write this term as minus dn of x by dx, f of x plus delta x minus f of x by delta x tending to 0. So delta x is very small value, then we can write this term as minus dn of x by dx, since n of x come in first term, so we are considering it as a minus term. So minus dn of x by dx into L bar. So n1 minus n2 is written as in this way, and substitute this value of n1 minus n2 in equation 1. So substitute this 2 in equation 1, and instead of n1 minus n2 we are writing phi n of x. So phi n of x is equal to, substituting 2 in equation 1, so minus of L bar into L bar is L bar square by 2 T bar into dn of x by dx. So this is electron flux density. So we can write, so we obtained phi n of x as minus L bar square by 2 T bar into dn of x by dx. So this L bar square by 2 T bar can be written as where L bar square divided by 2 T bar is equal to dn. This is known as diffusion, electron diffusion coefficient. Electron diffusion coefficient. So L bar is actually the differential mean free length and T bar is the mean free time. related with the collision. So this can be L bar square by 2, T bar is dn. Dn is electron diffusion coefficient. So therefore electron flux density phi n of x will become minus dn into dn of x by dx. This can be equation 3. So we obtained the value of electron flux density, so we can found the value for the net flow of electrons, that is electron flux densities we have got, and so we can define the electron diffusion current density. Diffusion current density. We can define electron diffusion current density, that is Jn diffusion, as the charge of electron that is minus q multiplied with the electron flux density. So electron diffusion current density means the charge of electron multiplied with the net flow of electrons per unit area, or the electron flux density phi n of x. So substituting equation 3 in this, we will get q into minus will become plus q into dn into dn of x by dx. So this is the expression for Jn diffusion. Similarly, the whole flux density phi p of x. So the whole flux density phi p of x can be written as minus dp into dp of x by dx. Similar analysis to that of electrons, if we do, then we will get phi p of x as minus dp into dp of x by dx, where dp is the whole diffusion coefficient. Dp, this suffix d suffix p, is the whole diffusion coefficient. Substituting this value in the whole diffusion current density, whole diffusion current density that is Jp diffusion equal to charge of hole, that is plus q multiplied with phi p of x, which is equal to minus q into dp into dp of x by dx. So this is the value for Jp diffusion. So we have obtained the value for electron diffusion current density and hole diffusion current density. So we can conclude the total current density, the total diffusion current density J diffusion is equal to Jn diffusion plus Jp diffusion, and this is equal to q into dn into dn of x by dx minus q into dp into dp of x by dx. So this is the expression for total diffusion current density. And so we have to define the total current in semiconductor. So we can define the total. We have studied both the carrier transportation mechanism. So the total current in a semiconductor, J can be J drift plus J diffusion. This is the total current due to diffusion and drift, where we have studied J drift as J drift is Jn drift plus Jp drift. So the total drift current is due to electron drift current plus hole drift current. So drift current equation is sigma E. So this can be written as sigma. Sigma means Q into N into mu N. This is sigma due to electrons into electric field E plus Q into P into mu P into electric field. So this is Q into N into mu N plus mu P into electric field. So Q into N into P. This is Q into so this is the total drift current. So actually this is not needed. This equation itself you can study. Qn mu n electric field plus Qp mu p electric field. And similarly we can write J diffusion as Jn diffusion plus Jp diffusion, and this is equal to Q into dn into dn of x by dx minus Q into dp into dp of x by dx. So these are the equations we have to study in deriving carrier transportation mechanism of drift and diffusion, drift current equation and diffusion current equation. And at equilibrium we can say that the drift plus diffusion, Jn drift plus Jn diffusion will be 0. So for electrons and for holes. So at equilibrium we can say that Jn drift plus Jn diffusion is equal to 0. Similarly, Jp drift plus Jp diffusion is equal to 0. So these are the two equilibrium conditions: the drift current plus diffusion current due to electrons, and the hole drift current plus hole diffusion current value will be equal to 0. So these are the different carrier transportation mechanism in semiconductors: drift mechanism and diffusion mechanism. Okay, thank you.